Thank you, Brad. All right, thank you, PyTexas. My name is Peter Sobot, and I'm here to talk to you today about working with audio in Python. So first off, who am I and why am I up here talking to you? Well, I'm a staff machine learning engineer, and I work at Spotify in what's called our Audio Intelligence Lab. That's a machine learning research team that uses machine learning to try and build systems that understand music and understand audio. We use a lot of Python day to day, which is why I'm here talking about Python. And we also build a lot of stuff that ends up in the Spotify app itself. So if you're a user, thank you. You've probably seen our work. If you're curious about other stuff we do, though, we publish APIs, such as this one that allows you to find out the tempo and the key and the beats and all sorts of stuff like that about every song that you might hear on Spotify. But we also publish machine learning models. We publish open source software like this called Basic Pitch. Basic Pitch here is an automatic transcription model. So you can put music or an audio signal in, and you can get notes out the other end. So it'll tell you which notes were played in a specific piece of music. Super cool, totally open source, totally free to use, runs in the browser, runs in Python, wherever you want. Find that on GitHub. But also, and more related to Python for today, we build audio software like this. This is Pedalboard. You can find this on GitHub. It's a Python library for working with audio. And we'll be touching on this later on in the talk. But first off, this is PyTexas, not Audio Texas. So I'm going to set some ground rules to start with. I'll talk about how digital audio works to begin with. Then once I've done that, I'll talk about how to read and edit audio in Python, how you can use audio in your own Python code. Then I'll talk about different problems you might run into working with audio in Python, gotchas or issues that you won't find out until it's 4 in the morning and you just got paged. And then I'll finally talk about how to make your audio code simpler by using Pedalboard, that library I just talked about. So let's start at the very top. I'm going to assume that you know nothing about audio whatsoever, and we'll talk about how digital audio works to begin with. Audio is really just a recording of sound, and sound is what you're hearing right now, I hope. And so to get that sound from the air around us into a computer, we're going to have to measure it in some way. So I'm going to put a two-dimensional graph on the screen here, and along the x-axis we'll have time in seconds, and on the y-axis we'll have pressure in the air. The pressure can move back and forth. You can have no pressure, you can have pressure coming towards you or going away from you. It doesn't matter too much, but I'm going to play a sound here, and we'll see how the pressure changes on this graph. Cool. So we just measured a whole bunch of points on this graph here. Each of them doesn't really have much meaning on its own. We can't tell what's going on without looking them all together. But what we can do is measure both where they are on the x position and on the y position. On the x position here, we can see that we measured 1 point roughly every 0.4 seconds or so. If I take the reciprocal of that, that gives us a rate of 2.5 points per second, and we can call that our sample rate. That's going to be super important later on. This is how we can tell how fast these points came in, and if we want to play them back through a speaker again, we need to know that number. Also, you might notice that these are spaced evenly around some middle point, and that's actually the silence point, or the 0 point on this graph. And that's because, like I mentioned before, pressure can come towards you or move away from you. And so maximum loudness or maximum pressure is actually at the top and bottom of this graph, and that's how we can read this. And then we can just measure each of these points. So on the left here, this point is maybe 60% amplitude or 60% of the maximum in the positive direction, so we could give it 0.60 there. And this point here is 90% amplitude in the negative direction, so we'd give it a value of negative 0.90. So I could join all these points together and try to reconstruct that original sound that we just heard of that saxophone, but you might notice there's not really that much detail here. We can't tell much from these 10 or 12 points, and that's because we didn't sample often enough. So let's try sampling the signal again, recording it again off the microphone, but this time I'm going to sample at a rate of 44,100 points per second, or 44,000 kilohertz, or sorry, 44.1 kilohertz, and that's actually the rate that most digital audio systems use today. And let's see what the difference looks like. So we've got a lot more data there, and we can already tell that visually because there's so much more detail in this waveform here. I can zoom in, and we can go from kind of the grand scale where we see multiple seconds at once, all the way down to the millisecond range. And at this range, we're actually going to be able to see the individual waveform, or sorry, the individual waves that make up the waveform here. If we were to measure the distance between these peaks, that would actually give us the pitch or the frequency, but I don't want to stop there. I want to keep going even further down to see exactly what the computer saw. And so we're going to go down to the microsecond level. Between each of these points here, we're actually looking at only 22 microseconds of time, which is a very, very, very small amount. And what the computer did here is that it measured the amplitude, or it measured the pressure, at each of these 22 microsecond samples here. And so if we take just those numbers, well, that's really the secret. That's digital audio. That's all there is to it. Digital audio is just streams of numbers, plus also that sample rate I mentioned earlier. So we've got some digital audio. We recorded this off a microphone. Technically, this is part of a saxophone clip. That's great. What can we do with it? Well, we could save these numbers on disk, and we could save them as regular uncompressed floating point information if we wanted to. We could use NumPy and Python to save these if we wanted to, and that'd be great. But that would cost us a lot of data. That would be about 21 megabytes per minute of audio, which doesn't sound like a huge amount if you have a laptop that has a lot of storage on it. But if we're talking about streaming music to your phone, 21 megabytes per minute is a lot. So instead, back in the 1990s, some extremely smart people came up with compression algorithms. And you might have heard of some of these before, things like MP3 and Ogg-Vorbis and AAC and so on. And these compression algorithms throw away part of the signal. So instead of storing every single number in its full resolution, we're instead storing a compressed version of that that is a little bit less high fidelity. It throws away stuff that our ears can't hear super well, but it gets our data rate down to less than 1 megabyte per minute in many cases. So that's how most audio is stored nowadays, and if we want to read that, we're going to have to use some sort of tool or some sort of library to decompress the audio for us. So let's start writing some Python. This is where I start to bring in actually Pedalboard, which is the library I mentioned earlier. So let's, at the very top, do from pedalboard.io, import audio file. Now, I don't want to talk too much about what Pedalboard does just yet, but here we're just going to pull in a class that can read the audio off of the disk and decode it for us. So if you've ever opened a file in Python, you're probably aware of using a with statement and the open constructor, or the open function. And here we're going to do the same thing, only we're going to use audio file instead. So I can say with audio file, my favorite song.mp3 as f, and I've just opened a file pointer that points into this file. Now, f has a couple properties on it that you won't find on a regular open file. For instance, you can find out the sample rate, which we talked about before, and see that this audio is recorded at 44,100 samples per second. We can also find the number of channels that are available in the audio file. In this case, it's a 2-channel audio file. It's in stereo, and that's because we have 2 ears. Usually we record in stereo. And just like a regular open file, we can do f.read on this file. And here we're going to ask for 3 samples rather than 3 characters or 3 bytes, and we end up getting a multi-dimensional array back. Now, if you're not familiar with multi-dimensional arrays, that's totally okay. They just look like this. You can think of them like lists of numbers. And the only property that's important is that the inner lists all have to be the same shape or the same length. So here, because we have 2 channels, we have a multi-dimensional array of 2 dimensions. The first is the number of channels, and that's 2. And the second is the number of samples, and that's 3. So here we have the left channel up top and the right channel at the bottom. So we'll touch up on this again in a second. If it doesn't make sense yet, don't worry about that. Okay, so let's try to do some more complex slicing and reading of the audio here. Let's start by opening up the file again, and then we'll read the entire thing in. Instead of just reading 3 samples, we'll read all of the samples in the entire file. And again, we end up with a multi-dimensional array. The first dimension is the number of channels, which is 2, and the second is the number of samples, which here is 1.3 million, which sounds like a lot, but if you divide that by the sample rate, that's really only 30 seconds worth of audio, so it's not that much. Then we can use standard Python array slicing tricks here. We could do audio at 0 to give us the left channel, and audio at 1 to give us the right channel. We can also do multi-dimensional array slicing like this. So we can pass an empty slice for the first dimension, and then pass up to 100 samples for the second dimension, and that'll just chop the audio down to only 100 samples in both the left and right channels. And we're just dealing with NumPy arrays here, so if you're familiar with those, everything transfers to this. We can also work in units of seconds instead. So we can say audio in both channels up into 10 seconds by multiplying 10 by f.sample rate, and we get a buffer that just contains the first 10 seconds. Standard Python slicing tricks apply, so we can do negative f.sample rate times 10, and so on, and everything just works as you'd expect. But just like a regular open file, why would you read the whole thing in if you only want part of it? Well, you can also deal with that here too. You can do f.seek to move around the file pointer in the file, and then you can do f.read just to read a certain section that you care about. And Pedalboard will just avoid decoding the audio that you don't need. So that's how we can open these files and read from them and play around with the data inside. But now let's change how they sound. I'm going to delete all of this, and then we're going to try to add an effect to some of this audio. So here, still dealing with my favorite song.mp3, we'll read the whole thing. I'm just going to take one of the channels, so I'll just take the first channel, doesn't really matter which one it is, and let's add an echo effect, or a delay effect to this audio. I'll define some parameters up front first. So we'll say delay in seconds is equal to 0.2. We'll add a delay here of 1/5 of a second. Then we'll also convert that from seconds into samples because we're indexing this array in units of samples rather than seconds. So this just makes it easier for us to do our math here. Then we'll set a volume parameter. This is how loud we want our echo to be. It'll be 75% of the original volume of the signal. Then we're going to loop through each of the samples here. So for every sample in our original array, we're going to do a little bit of calculation. I can explain this really quickly. We're just going to take the sample value at the current index, multiply it by the volume that we want, and then add it to the signal in the future, moved forward by delayed samples. And if that doesn't make sense, that's okay, because we're dealing with audio code, which means we can listen to it to find out if we did the audio code correctly or not. So here's two samples. The one on the left has not been run through our code, and the one on the right has. So let's take a listen to these. So that's before we run our code, and then here's after. You can hear that, right? That's definitely an echo effect. We've just added this kind of almost musical galloping kind of effect. And all we had to do was add the signal to itself here with these 6 lines of Python code. So it's not too complicated to add these effects, but let's try a different style of effect. Instead of a rhythmic effect, let's change the character of the sound itself. And in this case, I'm going to use a totally different sample as an example. Let's load up cool guitar.wave here. I'm going to read just the left channel as well. And then let's set some other parameters here. Let's set a parameter called gain to 200. This will be some distortion that we want to add to the signal. Then let's set volume to 10%. This is just going to make sure that we don't blow out the speakers in this auditorium, because distortion will make things a little bit louder. Then, for every single sample in the audio file, we're going to apply a mathematical function here. This happens to be math.tanh, or the hyperbolic tangent function, but that doesn't matter too much. If you don't know what that means, I don't really either. That's fine. All I know that this does is it'll make the sound much more distorted. And so let's listen to a before and after here as well. And after. So hopefully you could hear the difference there. What we did was really just multiply this signal by the distortion factor, put it into a function, and then reduce its volume. And that added a lot more aggression, a lot more overdrive to the signal. And all we had to do was write these 5 lines of Python code. Okay, so we've seen how to open audio files, how to edit them, how to manipulate them in Python. That's all pretty simple. But let's talk about some problems that you might run into when working with audio in your Python code. These are probably only going to bite you once your code has already been deployed and once you think everything is going well. So let's write a very quick 5-line application that can open up an audio file and make it louder and then save it back to disk again. So let's start by opening up myfavoritesong.mp3 again, and let's read the entire thing into memory here with audio equals f.read, f.frames. Then, once that's done, we'll multiply every sample by 2 to make every sample louder, and the whole thing will come out sounding much more loud. That's it. And then we'll save back to disk again by opening up audio file again. We'll pass W as the second parameter, just like you would with a regular open call in Python. We'll pass in the sample rate, and then we'll do o.write louder audio. Side note, this will encode an MP3 for us. So if you want to do MP3 encoding in Python, those 2 lines will do that for you, no problem. And then you deploy this code, and you send this to your users, and everybody uses it, and they're happy, and that's all great. But this code will probably crash eventually if you accept any user input or deal with audio files that you don't control or anything like that. And that's for one very simple reason. It's that MP3 is a good compression codec. So are many other compression codecs. And if myfavoritesong.mp3 here is 2 hours long, then as soon as you're reading the entire thing, you're going to have to decompress that audio. And in this case, a 2-hour input clip is going to require 2.3 gigabytes worth of memory. And you would have no idea, because all you're doing is opening the file and reading it in. So instead, we can write much more robust code by avoiding the need to read the whole thing into memory. And let's try doing that here. We can do that in only 2 extra lines of code. So I'll start by defining a chunk size. We're going to process the audio in chunks here, because there's no need really to read the whole thing in at once. We'll open our input file, then we'll open our output file and keep them both open at the same time. So now we're able to read from the input, do some processing, and write to the output. Then, as long as we have more input to read, so while f.tell is less than f.frames, we're going to read one chunk of the file, we're going to make it louder, and then we're going to write that to the output file. So this is 7 lines of code instead of 5 lines. Those 2 extra lines, I mean, that's a penalty we're going to have to pay here. But the benefit is that we're never going to use more than 4 megabytes of memory. And that's because we're only ever reading in one chunk of audio at a time. So my favorite song.mp3 could be a full collection of symphonies that's 12 hours long, and this code would process it just fine. So my takeaway for you here is you should always, always, always think of audio data as a stream. Audio is a stream. It's a representation of sound, and sound goes on over time, and time continues indefinitely. So you should always make sure that your audio code can handle any size of input. Okay, so that's a memory problem you might run into. Let's talk about a different problem though. Let's talk about a performance problem. Here's that example that we used earlier to add distortion to a guitar signal. This sounded just fine. It actually ran pretty quickly. Everything went well. But let's time part of this code. In fact, let's time this hot loop here, where we're going through every single sample of the audio file and applying map.tanh. If I time this on my MacBook here, we see that it takes 8 seconds per minute of audio to process this audio. That's 7.5 times faster than just playing the audio in the first place, or what we would say is it's 7.5 times real time. And that's great. Faster than real time is still really good. But if I were to rewrite this using something like NumPy, let's say, we'd find that NumPy performs a little bit better. And just writing it like this, almost the same exact code, this runs in 23 milliseconds per minute of audio. So let's do the math on that. We find that it's 338 times faster to use NumPy here instead of for loops, which should be no surprise to anybody who's dealt with Python for a while. It turns out that Python code is very, very slow if you're doing repeated numeric operations like this. Of course, because every line of Python you run has to invoke the interpreter, has to do a whole bunch of overhead that you don't really need if you're just doing the same operation on audio samples or doing math like this. So what I want you to take away from this is that for pure audio code, Python is slow. If you ever find yourself iterating sample by sample or operating on every individual data point here, you're probably doing something that's not going to scale, and that will become a bottleneck in your code. Instead, you should find a way to outsource that computation to another library, either something like NumPy that's very efficient, or something much more specific built for audio, like this one right here, called Pedalboard, which I happen to maintain, and which does a lot of this stuff for us. So let's take a look at how this can simplify your audio code. Now, a quick aside though, if you're wondering why this is called Pedalboard, do we have any guitar players in the room? I see one, I see, okay. Wow, there's a lot of guitarists here. Do any of you guitarists have pedalboards? Yes? Okay, good. A lot of people enthusiastic, great. So for those who are not guitarists, let me show you what I'm talking about here. Pedalboards are tools used by guitarists to change how their guitar can sound. Each one of these little boxes here is a different effect pedal, and these get chained together. So you can say, I want some distortion, I'm gonna click on this with my foot. I want some chorus, I'm gonna click on this with my foot, and you chain those together in different ways. And Pedalboard here is actually a library that was built originally to add audio effects to your audio. And so we called it Pedalboard, and it was a nice little metaphor. But let's take a look at what that looks like in Python code instead. So let's add an effect here using Pedalboard. Let's read in coolguitar.wave again. Even though I just told you in the last section never to read the whole file in, well, I'm gonna do it because this is a demo. And here, let's do from Pedalboard import reverb. Now, reverb is an effect that makes your audio sound like it was played in a larger space. You're kind of hearing some reverb right now in this room, but you'll hear even more in just a second. So I can do reverb equals capital R reverb here to create a new instance of this class. I'll set the room size to 75%, and then I'll pass this audio into the reverb plugin by just calling it like a function. So reverb, pass in audio, pass in the sample rate, and now I've just applied the reverb effect. So let's listen again to a before and an after here. Here's the before. And here's after that effect. Hopefully you can hear that. That's definitely a different sound. It sounds like we played that same clip in a big boomy cavern, and all we needed to do there was really apply 3 lines of Python code. But it doesn't really stop there. It's rare that you want to apply a single effect to your audio. It's much more common that you need to apply multiple effects, or you want to chain them together in some way, just like those pedalboards I talked about earlier. So Pedalboard has a facility for that, excuse me. And all we need to do there is create a Pedalboard object and pass multiple plugins into it. So we'll start by adding a distortion plugin, which is actually doing the same thing under the hood that we wrote in Python earlier. We can then add a delay plugin, which does the same thing as we wrote in Python earlier. And then we'll add a reverb plugin, which we just heard on the last slide. So with these 3 in order here, we're now able to apply the effect to, or sorry, all 3 of these effects to the same audio all in one fell swoop. And all we need to do is apply that to the audio by calling it like a function. And so we do that, and again, let's listen to the before and after. So here's the clean signal going into this function. And now with distortion and delay and reverb applied with these 5 lines of Python code. So that's definitely a very noticeable effect. It's a very musical effect. It adds this huge wash of sound. And all we had to do was import these effects from Pedalboard and call them on the audio data that we read in from that file. So very simple to do. But it doesn't stop there. If you've ever dealt with audio software on your laptop or online or anything like that, you've probably noticed that there's this vibrant community out there. All these people that are building what are called plugins or VSTs or audio units that you can import into your software to change your sound or to create new sounds. And Pedalboard actually supports using all of those too. So let's load a third-party plugin here that was not written in Python at all. I'll do from Pedalboard import load plugin. We're going to open up that cleanguitar.wave again, and then I'm going to load one of those plugins. I'll do plugin equals load plugin chowcentaur.vst3. This happens to be an open source guitar pedal emulation plugin. You can find this on GitHub. It's really, really nice. But it's also something that was designed to run in a digital audio workstation. It's not designed to run in the Python environment here. So it's got a UI. I can even do plugin.showEditor here, and a window will pop up. And I'm able to use my mouse to go and click on each of these knobs and turn them around and set the parameters how I like them. But if I don't want to do that, that's okay. I can also set the values for each of those parameters in Python code itself. So here I can print out the value that already exists for plugin.gain. I can set it to some new value. And I can also just pass audio into the plugin like I did before. So I do plugin, call it like a function, send in the audio and send in the sample rate, and it's applied to the audio. So let's take a listen one more time to before and after for this plugin. And just to remind you, I didn't write any Python code here for this plugin. This is someone else's native code, probably written in C++, that I just downloaded from the internet and imported here with load plugin. So that's the clean signal, and then once we put it through the plugin, that actually sounds pretty good. And again, no DSP code had to be written in Python. This is someone else's code, which is great. Okay, one more thing I want to show off. In the past year, there's been a lot of improvements in Pedalboard for doing things that are not just audio effects. For instance, now we can host instrument effects, or instrument VSTs and instrument plugins. For those who know audio software, that's a very, very different paradigm. We're not just changing the audio, we're instead creating new audio by passing in MIDI notes and telling the computer what to play at what time. So let's see that in less than 10 lines of code here. Let's load a plugin here called Magical 8-Bit Plug, which is an 8-bit synthesizer plugin that emulates the sounds of old Nintendo video games from the 80s. And I've just loaded that instrument. I can open its window again here by using show editor. And we can see that, yes, that is a different plugin there. Then, instead of passing audio in, I'm going to have to pass in a list of notes or messages. So here I'll do notes equals this list of MIDI notes. These correspond with C, E, G, B, musical notes. And I'll change those into MIDI messages here. So I'll send on and off messages for each of those notes to say, here's when you should start playing this note, and here's when you should stop playing this note. Then I'll open up an audio file to write to, and I'll render those notes by just passing them in like a function to the instrument and passing the output of that into f.write. And here's what that sounds like. So we just invoked a third-party plugin. We didn't write any of that rendering code ourselves, and that was less than 10 lines of Python. Okay, so I've got about 1 minute left. So I'm going to spend that last minute on a bonus round here, some advanced Pedalboard topics for anybody who is curious about audio or deals with it day to day. Some really cool things that you can do in Pedalboard that you might not have expected or might not have thought about. So far in this talk, we've been opening audio files by using the audio file constructor here, or the audio file function, and that's great. But it's very common for you to need to open an audio file and then read it in at a different sample rate than it was saved as. So instead of maybe 44 kilohertz, you might need it at 22 kilohertz or something like that. Well, Pedalboard lets you do that by just adding a little addition on the end of the call here. You can do .resampled2, and it'll give you a file pointer that behaves as if the file was saved with a different sample rate altogether. This is super useful. We use this all the time at Spotify. Extremely performant and extremely useful in production situations. On top of that, though, let's say you want to take some audio and time stretch it. You want to change how long it is or how fast or slow it is without changing its pitch. Or vice versa. You want to change its pitch, but you don't want to change how fast it's playing back. Well, all you need to do is from Pedalboard import time stretch, call this function with your audio, set the appropriate parameters, and you get the results there. Huge shout out to Chris Canham of Breakfast Key for implementing the rubber band time stretcher that we use here. It sounds great. And one last thing, all of the functions you've seen so far have been talking to files on disk, but you can also pass in file-like objects here. So you can render to a bytes IO buffer, you can render to a network stream, doesn't matter, it's all available right there in your audio file constructor. So I barely scratched the surface here. You can find it a lot more on GitHub at github.com/Spotify/Pedalboard. And I also have 5 minutes for questions, so please feel free to use the Slido to submit some questions, and find me after the talk to grab some stickers of this cool Pedalboard logo. Thank you so much, PyTexas.
Awesome. Awesome. Thank you, Peter. I'm intrigued. I'm not a guitar player, not a musician, but I now I'm inspired. I've got a stack of questions, so let's walk through some of these while they're getting set up for the next talk. First question, can Pedalboard work on live audio like a real pedalboard would?
That's a very good question. So we got this question so much that I actually put together a new feature in Pedalboard that does allow you to use it on live audio, actually just for a demo last year. It is now merged in, and you can use it with some restrictions. Look for the audio stream class online in the documentation if you want to use that.
That's awesome. We're going to unplug you here while we, okay. And if you want to grab the hand mic or pull that one out. Okay. So, next question. Any reason, let me think about this. Is there any reason for a stream not to just always use a chunk size of 1?
That's a great question. So you could use a chunk size of 1 if you're processing audio like this. At that point, the overhead of reading each chunk starts to dominate the runtime. So a larger chunk size will allow you to be a bit faster, but it'll use more memory. So there's always a sweet spot in there between processing speed and memory use.
Gotcha. Where do you find that sweet spot? Does it depend on sample rate, I guess?
It depends on the sample rate, depends on the machine that you're using. If you've got lots and lots of memory, like on the server, you'd choose tens of megabytes maybe for your buffer. If you're working in an embedded environment, maybe something much smaller than that.
Gotcha. Makes sense. Next, why choose Pedalboard over like a traditional DAW, like Audacity or Bandcamp?
Yeah, traditional DAWs are really great tools, and they're very good at allowing you to work with audio visually. Pedalboard is much more scriptable and much more easy to get integrated into your own software.
Okay, cool. You want to talk for a minute about the API design process for the package? And did it start as open source, or did that come out later?
Great question. So I'll tackle the second part first. Pedalboard was not open source to start with. It came from internal needs that we had at Spotify. And then we realized, oh, we built a tool here that many people could use, and we kept adding more and more to it. But for the API design process, I really came up with a lot of ideas from what you saw in Lynn Root's talk earlier about how to lean on familiarity when designing an API. So it tries to be as Pythonic as possible. And the idea is that if you know Python, all you need to do is swap out a couple functions and everything behaves like you would expect.
Yeah, I love the structure of opening it as a file and treating it like that normal file context. That's pretty smooth. You showed downsampling. Is it possible to upsample?
It is also possible to upsample. If you do upsample, there's no additional detail that will be added to the sound, though. Yeah.
Fair enough. Last one, then I think, Josh, were you about ready? Yeah, okay. Does it use FFmpeg internally?
I like FFmpeg, actually, but it does not use FFmpeg at all internally. It's all completely compiled code. There are no external dependencies. You just pip install it, and it works.
Okay, fair enough. You good? All right. Well, once again, thank you, Peter.
Thank you.